Okay, it's a pleasure being here again. I've been to Munich actually a year ago, and then before that, one of the EIKEs a few years back. So it's always a pleasure being here. I want to continue what others have already mentioned in previous talks, and that is that the sun has a large effect on climate. And I want to show you how the fact that the sun has a large effect on climate changes, or should change, the way that we understand climate change in general, and 20th century climate change and future climate change as well. So basically, to some extent, it's picking off where Professor Scafetta left in the previous talk. Okay, so how do I move the slides forward? Maybe with this. Okay, so I want to start by talking about what's wrong with the standard scenario that we always hear about, the global warming scenario that is advocated by the IPCC. The reason I want to do that is because when introducing a new picture for what the climate is doing, you want to know, the first response of people is, just a second, if you're saying that it's not what we hear about, it's something else, then you want to understand what's wrong about what we hear about. Like, is there any contradiction? Is there any clash that we should understand about, that we should know about? And in reality, whatever I'm going to say doesn't contradict anything that is based upon evidence. It only contradicts things which people claim not based upon evidence. Okay, so I'll start with the main arguments about the main arguments which people use in order to convince us that global warming is mostly because of anthropogenic activity, and that climate is very sensitive, and that global warming in the future is going to be catastrophic. And then I'm going to show you that these arguments don't hold any water. I'll show you additional problems that are present in the standard model, and we should have raised red flags a long time ago, but people simply do their best to ignore them. I'll show you evidence for the fact that the sun has a large effect on climate. You can actually quantify the effect that the sun has on climate and then use that to better model what has been going on over the 20th century, reach the conclusion that the sun has been important. Probably it explains between, say, half and two-thirds of the warming over the 20th century. And it also implies that climate sensitivity has to be on the low side. How low? If you open the IPCC reports, they'll tell you that climate sensitivity is somewhere between 1.5 to 4.5 degree increase for CO2 doubling. All the empirical evidence that you see, in particular, if you include the effects of the sun, points to a climate sensitivity which is only about 1 to 1.5 degree increase per CO2 doubling, which means that a business-as-usual scenario will give you a warming over the 21st century, which is modest. How modest? Well within the goals of set in Copenhagen or in Paris. So this is what I'm going to talk about. One of the things I'm not going to talk about is the actual mechanism, or maybe I'll just touch a little bit, the actual mechanism linking between solar activity and climate, and that's going to be the subject of my colleague, Professor Svensmark, in the next talk. What I want to emphasize is that it is not really important what the mechanism linking solar activity to climate is, because we see that such a link exists and that it's very large. It is extremely interesting academically for myself and for others to study what this mechanism is all about, because as scientists, we're curious creatures. But you don't need to know what this mechanism is to know that the sun has a large effect on climate and that it's important. Okay, so let us begin. Okay, the IPCC convenes every 6 years or so, they write a scientific report. What do they tell us? Well, they tell us that most of the warming over the 20th century is anthropogenic and that climate is very sensitive. Now, what is the basic arguments that you use in order to prove this point? It turns out if you try to distill all the arguments, all the science that you find in the scientific reports, you find that there are basically two main arguments that are being used to quote-unquote prove that humans are responsible for the global warming. And these arguments are wrong. And now, before doing that, I want to emphasize that there is also a lot of chaff, there's a lot of noise around us, which is just that. It's not doing anything towards the science, and we have to realize it's there. One of them is that, these are not arguments, these are pseudo-arguments. First of all, science is not a democracy. If you have an argument with someone and they tell you, look, 97% of the people say that it's this or that, it doesn't imply that it's so. It's totally irrelevant. 100% of the people could have said the Earth is flat. It wouldn't have implied that they're right. Okay, so any such argument is totally irrelevant. Other such arguments are arguments showing you that the climate has warmed. Okay? If you see a polar bear floating on an iceberg somewhere, it doesn't mean that it has warmed. It doesn't mean that it has warmed by humans. And it doesn't even mean that there are less polar bears. Okay, so there are a lot of such arguments which are totally irrelevant, and you have to realize it's just noise around us trying to interfere with the real science. Okay, so what are the two main arguments that the IPCC uses in order to convict, again, quote-unquote convict, humans in the global warming? The first is that the warming that we have seen is unprecedented. Okay? If it's unprecedented, it's likely to be unnatural, hence because of humans. Even if it was true, even if the warming was unprecedented, it's not necessarily proof that humans are the cause, because, we might be living in some kind of a natural fluctuation. It happens. But it so happens that it's not even unprecedented. The Middle Ages were just as warm as the 20th century. The unprecedentedness that we all hear about actually was highlighted in the third assessment report of the IPCC in 2001 through the hockey stick graph that we all know about. This infamous graph we now know using as a result of the ClimateGate emails, we know that this hockey stick is a hockey stitch where people stitched tree ring data up to 1960, beyond which they actually showed a temperature decrease. So they chopped it off, and then they stitched to this tree ring data the thermometer data. Okay, so they were stitching together two things that don't belong together. Okay, so the hockey stick is nothing. 20th century warming is not really unprecedented. There were other natural variations similar to that on timescales of thousands of years. So this argument is totally irrelevant. The second argument that people use is that without human effects on the climate, without the anthropogenic forcing due to CO2, we cannot explain the warming. If you simulate what has been going on over the 20th century, and you do the simulation twice, once with the anthropogenic forcings and once without the anthropogenic forcings, you find that without the anthropogenic forcings, you cannot explain the warming. Hence, most of the warming has to be due to anthropogenic forcing. However, this argument implicitly implies that there is nothing else, or implicitly assumes that there is nothing else that can explain the warming. But there is something which is as clear as daylight, and that is the sun. Okay, so the main arguments of the IPCC are flawed, and there is no other argument that can prove that CO2 has a large effect on the temperature. There's no other argument that the warming is necessarily anthropogenic. Okay, there's nothing. Okay, so let me now mention a few more inconsistencies that you find in the standard picture. Some of them are related to those two arguments, some of them are additional, some of them we heard actually in the talks before. So the first argument is that the 20th century is unique. As I told you, we know from the ClimateGate emails that the hockey stick graph that you see on the right is totally bogus. And in fact, there was a little ice age, there was a medieval warm period. It's actually funny, in 1990, the first IPCC report told us that there was those variations, and then suddenly in 2001, it's like in George Orwell's 1984, we woke up one day and history was changed. Yeah. Okay, so history didn't change. Okay, the second argument, which I mentioned, is the following. On the left, you see the radiative forcings that enter the global circulation models. You can plug them into numerical simulations, global circulation models, and then find that at the top, if you include anthropogenic forcings, you can explain the temperature increase. If you exclude the anthropogenic forcings, you cannot explain the temperature increase over the 20th century. Hence, humans are necessarily responsible for 20th century global warming. Again, this is flawed because it assumes that there's nothing else. But there is something else. It turns out that the sun is a variable star. Its output, its luminosity changes on various timescales. And not only its luminosity, also other non-thermal components of the sun change with solar activity. The timescales range from days over which we have eruptions at the solar surface through years. We have the 11-year solar cycle, and on longer timescales, we have modulations of the solar activity. The interesting thing to note is that the main variability of the sun is the 11-year solar cycle. It arises from the fact that every 11 years or so, the magnetic polarity of the sun changes, it flips. Okay, so the real cycle is actually 22 years. And with this variability, we get changes in things like the total solar output, the TSI, the total solar radiance. We get changes in the amount of UV. We get changes in the solar wind and other components. We get changes in the number of sunspots and so forth. Okay, so I stuck this slide in the wrong place. Anyway. What? Okay, so as I said, the evidence, there is no, not only is there is no evidence to support the standard picture, there is evidence to show you that it's wrong. Okay, so until now, I mostly showed you that there is evidence, that the evidence that is used to support a picture does not really support it, but there is also evidence that shows you that the picture itself is wrong. Okay, so the first thing which should have raised the red flag, and which was mentioned before, is the fact that the temperature increase we have witnessed over the past 2 decades or so is significantly less than what the IPCC models, the global circulation models, are predicting. Again, this should have raised the red flag, but instead, scientists conceive of various strange models to hide the heat in the oceans, or I don't know what. It turns out that Earth's climate sensitivity is low, and this heat actually escapes from Earth. It's not with us anymore. So this is a first indication showing you that climate sensitivity is actually much lower than what the IPCC is predicting. Another problem, which is basically the hotspot that we saw before in the previous talk, is the fact that models give you a predicted warming which is much larger at higher altitudes over the equatorial regions than warming elsewhere in the atmosphere. And this has to do with how CO2 affects the energy budget. CO2 is a greenhouse gas. It makes the atmosphere more opaque. So basically what happens is that the atmosphere is more opaque up to higher altitudes, and therefore the heating should take place also at higher altitudes. Other types of warming could give you different signatures, but the signature of the warming that we see with the signature of the warming that we actually see using radiosonde data over the past several decades is of a warming which is actually larger, closer to the surface than higher altitudes. So if there was any signature that could point to what the warming mechanism is, then the signature that we expect from CO2 is not consistent with observations. Another indicator that the climate is much more, that the modeled climates are much more sensitive than the real climate is the response to volcanic eruptions. When we have a large volcanic eruptions like Krakatau, like Pinatubo, and so forth, we have dust coming from the volcano into the stratosphere. It can sit there for a year or two. It reflects some of the sunlight, so it should cool the planet. And if you look at how much the models give you that the planet should have cooled, it is typically 0.3 to 0.5 degrees. This is the predicted cooling by the climate models. What's reality? In reality, if we look at the average temperature decrease in the several years following large volcanic eruptions, so this is the average global temperature in the several years preceding and after large volcanic eruptions, we see that at most the temperature reduction is about 0.1 plus or minus 0.1 degrees. That tells you that climate is significantly less sensitive to changes in the radiation budget than the models. Okay. We mentioned climate sensitivity. It turns out that it is, of course, the most important number characterizing climate, because with climate sensitivity, we can predict what will happen in the future. If, for example, we double the amount of CO2, we want to know by how much the temperature is going to increase over the 21st century. Is it going to be 5 degrees, or is it going to be 1 degree? So obviously, this number is worth several $1 trillion, because if we have known the actual value of this number, and I know what the value is, then we can save a lot of money, or we actually need to spend a lot of money. So why can't climate models predict what the value of the climate sensitivity is? It turns out that climate models have a real problem basically describing clouds. What do I mean? If we double the amount of CO2 in the atmosphere and nothing else in the climate would have changed, we know from just differentiating Stefan Boltzmann's law for black body radiation, we know that the 3.8 watts per square meter should have corresponded to a temperature increase of about 1.2 degrees Celsius. However, this assumes that nothing else changes in the climate. If, however, we warm the climate because we have more CO2, then we evaporate more water from the oceans. And if we have more water vapor in the oceans, water vapor is an excellent greenhouse gas, so we would amplify the temperature increase much more. Okay? However, if we have much more water vapor in the atmosphere, we can also have a much larger cloud cover. And clouds, they can cool and they can warm. Most clouds actually cool the planet because the effect from the reflection of the sunlight is more important than the blanket effect that they have. But it turns out that all the cloud cover in the climate models is described by recipes, okay? Numerical recipes telling us how much the cloud cover is going to change if you, for example, increase the temperature by a given amount or change the humidity by a given amount. So all the climate model sensitivities, if you try to predict what the climate model, what the climate sensitivity is going to be using numerical models, it all boils down to what is the recipe that you use in order to describe cloud cover. Okay? In computers, it's called GIGO, garbage in, garbage out. Okay. This graph actually demonstrates this point. Notice it's a graph from 1989. The situation hasn't changed much since then. What you see here is the climate sensitivity of various global circulation models as a function of one very important parameter, and that is the feedback that you have on the energy budget through a cloud cover when you change the temperature. This shows you that by far, the single most important uncertainty in global circulation models is the way that you treat clouds. If you don't know how clouds behave, you cannot predict climate sensitivity using global circulation models. Okay? GIGO. Now, this is the reason, this is probably one of the most embarrassing graphs that the IPCC should have had, but they don't have because, again, it's embarrassing. You see here the claimed climate sensitivity that Earth should have according to the IPCC report from the first report in 1990 until the last one. And you see that in all climate reports, they claim that climate sensitivity is somewhere between 1.5 and 4.5 degree increase per CO2 doubling. In fact, it goes back to a federal committee that convened in the US in 1979. They said, we think climate sensitivity is somewhere between 1.5 to 4.5 degrees, and billions of dollars and billions of euros and billions of Deutsches Mark, because before that it was Deutsches Mark. Later, we don't know the answer to the most important number in climate science any better. This is totally embarrassing. Interestingly, in the penultimate report, we were told that climate sensitivity should be somewhere between 2 and 4.5 degrees. You see, it's progress. But in the last report, I had to go back to the original range. And the reason is that if you assume that the sensitivity cannot be below 2 degrees, you cannot explain the lack of warming that we have seen over the past 2 decades. Okay, so some people realize that the hiatus is a problem. Okay, another problem is that there is no fingerprint that proves that CO2 has a large effect on climate. In fact, as I'll show you, there is the opposite. Now, some of you might say, just a second, I saw Al Gore's science fiction movie, The Inconvenient Truth, and in that movie, he showed us this graph where you have a CO2 reconstruction and temperature reconstruction from ice cores in Antarctica. Okay, and then he's told us that the relation is complicated, but we see that when there is more CO2 in the atmosphere, the temperature is higher, because he wants to convince us that CO2 has a large effect on the temperature. But who told us that it's this way and not this way? Okay, maybe it's the temperature affecting the CO2. What Al Gore didn't tell us is that when you have records with a high enough temporal resolution, which are usually records from Greenland, where ice is stacked much faster, in those records you find that CO2 tends to lag behind the temperature, okay? I don't think the effect of CO2 is so large that it can affect the temperature even before it starts increasing, okay? I don't think so. Basically, what you see here is the fact that there is most of the CO2 in the Earth system is CO2 which is dissolved as carbonic acid in the ocean. So there's about 50 times more CO2 in the oceans than there is in the atmosphere. And this equilibrium is temperature dependent, such that when we heat the oceans, we release CO2 from the oceans, and it goes out into the atmosphere. Okay? So what we are seeing here is just this equilibrium. Of course, CO2 has some effect on the temperature, but these correlations don't tell us anything about it. It turns out that on much longer time scales, there are changes in the CO2 which are not due to this temperature-dependent equilibrium, but it's due to the fact that you have CO2 coming from inside the Earth through volcanic activity on one hand, and then you have CO2 which settles down as limestone on the ocean seafloor, and then it goes down through subduction zones, and it's recycled in Earth and goes out in volcanic activity again. So over 500 million years that you see here, you see that there were very large variations in the CO2. How large? This is a logarithmic scale, and you see that there were variations of order a factor of 10, one order of magnitude. These are huge variations in the CO2. If CO2 has a large effect on climate, then there should be a correlation between the CO2 in the atmosphere and the temperature reconstructed over this time scale. Do you see a correlation between those two graphs? No, I don't either. The fact that there is no correlation between the CO2 reconstruction and the temperature reconstruction can be used to place an upper limit on the effect of CO2 on the average global temperature, and this upper limit is 1.5 degree increase per CO2 doubling, so just below the IPCC range. Okay, CO2 cannot have a larger effect on climate because otherwise we would have seen it. Okay, and then going back to the one of the two arguments at the beginning, it turns out that the sun has a large effect on climate, and that's the Joker card that changes the whole picture, our whole understanding of the 20th century. Okay, so evidence that the sun has a large effect on climate. This is one of the nicest correlations I know. This is carbon-14 from tree rings in all across the world. Carbon-14 is formed by cosmic rays, which are modulated by solar activity, so it's a proxy of solar activity. And at the bottom, you see oxygen-18 to oxygen-16 isotope ratios in stalagmites in Oman, in the southern Arabian Peninsula. Water with oxygen-18 is heavier than water with oxygen-16, and therefore the evaporation rate of water with oxygen-18 is slower than the evaporation rate of water with oxygen-16, but the ratios depend on the temperature. This means that changes in this ratio is basically a proxy of the temperature in the Indian Ocean. Okay, so you see that this is a proxy of solar activity, and this is a proxy of temperature in the Indian Ocean. Do you see a correlation between the two graphs? Yeah, so it tells you one of two things. Either the sun has a large effect on climate, or that climate has a large effect on the sun. Okay. This is another example, this time from the Northern Atlantic. You see, again, carbon-14 in blue, and then you see in black something which is called ice-rafted debris. You take cores from the ocean seafloor, and you can see cold years are years when you had icebergs float further south, melt, and leave their ice-rafted debris at southerly latitudes. So you can see a correlation this time in the northern Atlantic. So you have such correlations all over the world, telling you that the sun is affecting the climate all over the world. However, there is one correlation which not only shows you that the sun has a large effect, and again, all over the world, but you can actually quantify the effect that the sun has. Here you see in red the solar activity, so you can see the 11-year solar cycle, and in blue, you see the rate of change of the sea level. You see basically that when the sun is more active, the seas are rising. When the sun is less active, the seas are falling. Now, why is that? On short timescales, most of the sea level change is because of thermal expansion. About 80% of the signal you see here is thermal expansion. So what happens is that when the sun is more active, heat is entering the global climate system. When the sun is less active, heat is leaving the climate system. So you can use this not only to show that there is a very clear link between solar activity and climate, or vice versa. I'm just kidding, of course. The oceans don't affect the sun. So not only does it show that the link is there, it shows you how large is this link, okay? You can use satellite data to, again, show you that if you use the sun and El Niño, the El Niño Southern Oscillation, you can use the two things to explain the sea level change rate minus the linear trend, which was removed. Okay, so we have various data sets. I showed you two, the tide gauges and the satellite altimetry, but you have other data sets showing you that the sun has a large effect on climate. How large? Between solar minimum and solar maximum, the change is more than 1 watt per square meter. This is comparable to the anthropogenic effect. It is also much larger than what the IPCC is claiming the whole effect of the sun is. That tells you that if you go to this forcing graph, the IPCC tells us that the solar forcing is something like that. However, solar activity increased over the 20th century, and the total forcing that we should expect that the sun has had is much larger. In fact, probably larger than what the CO2 has been doing. Okay, so you cannot model the 20th century climate change without taking the sun into account. Okay? All the models telling you that the temperature will increase by a lot, that the Antarctica will melt, that the penguins will find themselves, I don't know where. They're all based on models which are not taking the sun into account and are therefore highly exaggerated. Okay, just a small side step. Henrik Svensmark is going to talk about the link at length. Today we know where this link, or how come the sun has a large effect on climate. The link is something which is quite indirect. Instead of the sun affecting directly the climate, the sun affects the climate through the fact that it has a solar wind. It's a very tenuous wind that is ejected all the time. The sun is losing 10 to the minus 15 of its mass every year. But this wind modulates the flux of high-energy particles which come from outside the solar system, particles which are called cosmic rays. They actually come from the death of massive stars. When a star is more massive than about 10 times the mass of the sun, it dies in a huge explosion called a supernova, and these explosions accelerate cosmic rays. It turns out that these cosmic rays are the dominant source of ions in the troposphere, in the lower part of the atmosphere. This means that if we have more supernova around us, we get more cosmic rays. If the sun is more active and it has a stronger solar wind, we get less cosmic rays reaching us because the solar wind blocks some of the cosmic rays. Basically, because of the solar wind, the cosmic rays lose energy. So today we know that the link is the following. When we have a more active sun, we have a stronger solar wind, we get less cosmic rays and therefore less ions in the atmosphere. Today we know that these ions play a role in the nucleation of small condensation nuclei, particles which are typically 2-3 nanometers in size. And the ions play a role in the survival probability of these aerosols as they grow to become large particles, which are needed when you want to condense water and form clouds. So when you have a more active sun, you have a stronger wind, you have less cosmic rays, less ions, less production of small aerosols, less of their survival into becoming large aerosols, and then when we reach 100% humidity, the clouds that we get have less droplets. If clouds with fewer droplets have a smaller surface-to-volume ratio, so they reflect less of the sunlight, and therefore, if they reflect less of the sunlight, more of the sunlight penetrates into the climate system, and it warms us. Okay? It sounds a little bit indirect, but today we have evidence for every single piece of this link. For example, if you have a large gusts in the solar wind, called Ford-Bush decreases, you get, well, the gusts are not called Ford-Bush decreases, they're called coronal mass ejections, but when you have such large gusts, those gusts in the solar wind reduce the flux of cosmic rays reaching the Earth for several days, and these are called Ford-Bush decreases. We can see that as a response to this change in the cosmic ray flux reaching the Earth for several days, we have a reduction in the number of aerosols over the oceans or various other cloud parameters. The clouds on Earth react to these short-term reductions in the cosmic ray flux. We also have evidence from a much longer time scale. On very long time scales, our environment around us, around the solar system, changes because sometimes we are in the vicinity of more supernovae, or more formation of stars, and therefore more supernovae, and therefore more acceleration of cosmic rays. And sometimes we are in regions of the Milky Way where you have less star formation, and therefore less supernovae and less cosmic rays. You can reconstruct the cosmic ray flux over the past 500 million years. Actually, you can do it over the past billion years, and see that every 150 million years or so, we passed through a spiral arm of the Milky Way, and every time we did that, the cosmic ray flux on Earth was higher. The interesting thing is that every time the cosmic ray flux was higher on Earth, the temperature on Earth was lower. Okay, so over the past billion years, we have had 7 epochs of ice ages. These are epochs during which we had some glaciations on Earth. In between, we had periods, like 100 million years ago, where you didn't have any glaciations on Earth. You could find alligators sunbathing in Alaska and enjoying themselves. Okay, you cannot find alligators in Alaska anymore. Okay, so it turns out that these warm periods correspond to the times when we were in between spiral arms, when there was relatively little star formation next to us. So we see that there's a lot of evidence showing you that cosmic rays affect the climate. Here is another piece of evidence. When we roam the galaxy, not only do we pass the spiral arms every so often, we are also, like a dolphin, moving up and down perpendicular to the galactic plane. If cosmic rays have an effect on climate, we should expect that when we are close to the galactic plane, the temperature should be low. When we're further away from the galactic plane, there are less cosmic rays because they diffuse from the plane outwards, And if there are less cosmic rays, it should be warmer on Earth. Do we see that in the data? Well, actually, of course we see that, otherwise I wouldn't have asked you this question. Here, this is the raw oxygen 18 data I showed you before. This is just a long-term systematic offset, and this is the 145 million year oscillation due to the spiral arm passages. But once you remove that, so you basically do a high-pass filter, you find these temperature variations. Now, these temperature variations are nicely explained with this oscillation, the blue curve, which is what you would expect from the fact that we are oscillating perpendicular to the galactic plane. Okay, so not only do we see that the sun has a large effect on climate, we see that it is through cosmic rays. How do we know that? Because when we see independent variations of the cosmic rays, which are unrelated to other things, whether it is because of very short-term variations in the cosmic rays because of the gusts in the solar wind, or if it's very long-term variations in the cosmic ray flux, which has nothing to do with solar variability, we find that these variations in the cosmic ray flux also translate into changes in the climate. Okay, so cosmic rays have a large effect on climate, and that's the link between solar activity and climate. Okay, what does it tell us? The standard picture is basically the following. We know that the temperature on Earth over the 20th century increased by almost a degree. The standard picture tells us that it's mostly because of anthropogenic forcing. This means that you need a climate which is relatively sensitive in order to explain the observed warming. Okay, you need a large, you have the relatively small changes in the energy budget, which is what we humans have imposed, times a large sensitivity will give you the large, it's not large, the observed temperature variation of about increase of about 1 degree. But if the climate sensitivity is large, then any scenario over the 21st century, for example, if you double the amount of CO2, it would necessarily give you a large temperature increase. However, we know now very well that in addition to the anthropogenic forcing, we have also the solar forcing, which has been probably even larger than just the CO2. This tells you that if you want to explain the observed warming with now a much larger total net radiative forcing, you need a climate sensitivity which is on the low side. Okay? This low climate sensitivity is actually consistent with the empirical data. For example, the response to volcanic eruptions or to the lack of response over geological time scales where you don't see any correlation between CO2 and the temperature. Okay, so you have a picture which is much more consistent. Okay, you can actually build a climate model which includes diffusion into the oceans and interaction between land and oceans and things like that, and leave the climate sensitivity and the solar forcing as free parameters. And you can ask the question, what are the climate parameters that would explain what we have seen best? And when you do that, you can fit 20th century climate change much better than models you find in the IPCC reports. And of course, the reason is because you allow the sun to have a large effect on climate and therefore explain things like the temperature decrease from the 1940s to the 1970s, something which is very hard to do in standard models. So the residual that you get in such models is typically half as much as what you get from standard climate models. So you can explain the 20th century much better. You can then use it to integrate forward in time, and when you do that, you get predicted temperature increases, for example, for a vanilla-flavored business-as-usual scenario, and you can compare that to the IPCC models and see that the predicted temperature is much smaller. Future climate change is going to be much more benign. Okay, and again, the reason is that if you include solar activity, you need to explain things, you need a lower climate sensitivity, and therefore future warming should be much smaller. Okay, so let me summarize. There are no arguments, or there are no valid arguments that necessarily prove that the standard picture is correct. So whatever I said now is not really inconsistent with anything you find in the data you find in the IPCC reports, not with the claims that they derive from that data. Okay, there's nothing inconsistent between what I said and any data, piece of data that you can find in the IPCC reports. The biggest difference is that in the IPCC reports, they ignore the large effect that the sun has on climate. But if we include that, we find a much more consistent picture for what has happened, one which is more benign, as I said. Okay, so we know the sun has a large effect on climate. We know the link is through cosmic rays. And I leave the floor to my colleague, Professor Henrik Svensmark, to talk to you about the link itself.